method, traditional method. But for our studies, we consider this a problem because our systems are different from traditional systems. Because right now, nowadays, machine learning developed quickly as a very advanced performance. So machine learning techniques have been integrated into the autonomous systems. This integration defines the new generation of autonomous systems. This is called the learning-enabled autonomous systems. For example, here are the test beds in my research, like the robots and like the CPU card. So machine learning here has been used for the computer vision, for perception part, has been used for the test planning part, has been used for the control part. So here you can notice machine learning right now can influence almost all kinds of the components of these autonomous systems. So the issue is we introduce machine learning here. The critical reason is machine learning can bring us the super performance, but no one can deny this. If you know this super performance, well, we need the machine learning, right? That is a related issue. So, but if we look at the safety, we consider the safety evaluation. This is another story. So here you can use in your Google search, just type these keywords, AI incidents. You can immediately got this open data set. This data set records the real everyday incidents and also has a long record of the historical AI incidents. You can check a significant part of these incidents are related to this learning-enabled autonomous systems, like the Tesla self-driving vehicles, robots, many such examples. So this real example demonstrates learning-enabled systems are facing new safety challenges. So here we identify 3 critical safety challenges that is because of this machine learning. So the first challenge is, that deep neural network, right? Deep neural network, its property is it has huge space of parameters. Its activation is nonlinear. Because of these properties, the deployed DNA for your perception, for your planning is very hard. Its behavior is very hard. It's very hard, it's very to predict. It's so complex. It's one challenge here. The second challenge is the DNA. It has so many parameters, Latin variables, but they typically belong to the purely data-driven approach. Purely data-driven approach are very sensitive to the spurious correlation. Spurious correlation means the wrong correlation, but it can happen in the purely data-driven DNA. The last challenge is for our study, our application domain is safety critical physical engineering systems, like the airplane, the UAV, the drone, the robots. These systems, their system dynamics, their behavior are governed by the deterministic physics law. For example, this physics law can include the force balance equation, the Newton motion law, and the energy conservation law. These laws are deterministic. These laws are validated, well validated. But many machine learning models, they are probabilistic models. So in this domain, if we are using probabilistic model to do something, to do some decision making for this probabilistic model, definitely this model, his input and output sometimes can violate the physics laws. So of course, you can argue, yes, it can violate the physics law, but its probability is very small. Yes, but it can be corner case. But remember that our application is a safety critical system. It's safety critical system. A corner case can lead to, can result in disaster. It can kill many persons, like the airplane crash. So that is a very challenging programs. Our collaborators also include the Hoodra Boeing. We also are facing these programs, right? So we do not fully trust the purely data-driven because corner case can happen. It's a corner case, the probability is small, but it can happen. If it happens, it can kill hundreds of persons or customers. So here, these are three safety challenges we have, identified. So the question is, we identified the challenges, safety challenges, how can we address them? So our solution is physics AI. Physics AI, in other words, means we do not fully trust data-driven AI. So here, I would like to first present our concept or our definition of the physics AI. What is the definition of physics AI? So to address the same mission, we have the traditional method, that is physics model-based design. This is traditional method. We also have the current popular data-driven machine learning design. But achieving the same mission, both of them have their own limitations and also their own advantage, like I list here. So the question here is, do the same things. What can happen if we integrate them? So this integration generates our first concept of this physics AI. So of course, our physics AI also have other components. This definition is very high level, is very simple. Our physics AI also have other components, our design components, such that physics AI it can overcome both of their limitations and to take over their advantage. So here, that is our first generation of the physics AI. Because we have technically different works. So today I would like to use this deep reinforcement learning framework to explain how can we incorporate physics knowledge into the purely data-driven deep reinforcement learning to generate this physics AI. So this is our current framework of this physics-regulated deep reinforcement learning framework. So here, this design has three novelties because these three novelties are invariant embedding designs. The first invariant embedding design is called the radio action policy. Here, the second novelty is invariant embedding design 2, that is safety embedded rewards. This safety embedded rewards is a construction based on our physics knowledge. Finally, we propose this physics knowledge enhanced DNA. This DNA is the building block of this critical network and active network for this physical learning. So that is the general framework. I'm going to detail these three designs. So before that, I would like to present this mathematical formula